Let's understand the history of geometry. When we say geometry, we understand that people have defined what is point, what is line, what is line segment, what is triangle, what is circle. But the first intuition to understand those things was what was the motivation behind that thing?
Geometry's roots lie in the practical needs of ancient civilizations. Early humans observing the physical world, fields, rivers, stars, needed to measure land, build structures, and track celestial patterns. The idea of a point likely arose from marking locations on land. Lines and shapes emerged from practical tasks, dividing fields, drawing boundaries. Over time, these practical needs sparked curiosity, leading to deeper exploration of patterns, relationships, and logical reasoning. In short, geometry began as a way to solve real world problems, and its abstraction grew from there.
One example uh, that will relate everything in detail.
A classic example is ancient Egypt. They needed to restore field boundaries after the Nile's floods. To do this, they developed techniques to measure land. For instance, they used ropes with knots to form right angled triangles. This practical rope stretching gave rise to rules for right triangles, foreshadowing what we call the Pythagorean theorem. Over time, these practical measurements turned into abstract geometric principles. What started as land surveying evolved into a formal study of shapes and space.
Okay, what about Pythagoras?
Pythagoras and his followers around the 6th century BCE took geometry from the practical to the philosophical. They believed numbers and ratios underpinned the universe. Pythagoras' famous theorem, that in a right triangle the square of the hypotenuse equals the sum of the squares of the other two sides, went beyond measurement. It revealed a universal truth about shapes. This shift, seeking eternal principles, transformed geometry into a cornerstone of mathematics and laid the groundwork for all theoretical geometry that followed.
So this, I would say this geometry is very useful and give one practical implication. And how did Pythagoras thought in the first hand?
Absolutely. One practical implication of Pythagorean thinking is still seen today in construction and architecture. When builders ensure walls meet at right angles, they might use a 3-4-5 triangle, a Pythagorean triple, to confirm perfect perpendicularity. As for how Pythagoras thought in the first place, he was deeply influenced by observing patterns in nature and music. He believed harmonies in music corresponded to simple numerical ratios, and he extended this belief to shapes, thinking that the universe itself had mathematical harmony.
Oh, they can easily see the 3, 4, 5 triangle triplet and see the right angle triangle mid. That's a clear-cut observation.
Exactly. It's a simple, tangible application. They'd measure out, say, 3 units on one side, four on another, and ensure the diagonal is five. If it is, they've got a right angle. No need for fancy tools. It's amazing how far back that practical wisdom goes.
What about, can you think of next big geometrical figure that
Well, if we think historically, the next big leap was likely the circle. Ancient cultures saw the sun, moon, and wheels, and circles became central to understanding motion and symmetry. This fascination led to concepts like pi and the idea of perfect symmetry. From there, geometry branched into more complex curves and eventually the conic sections, ellipses, parabolas, and hyperbolas, which became essential in everything from astronomy to engineering. Each step built on earlier shapes and deepened our understanding.
but I think sun is a mode of a sphere and moon is also a mode of a sphere. But when we see from the earth, it look like a circle. That's how they observe things and make something that if we give a finite amount of radius like thing, a finite length, and if we rotate that, we get a similar geometrical figure like that.
Exactly. That's a beautiful insight. From observing circles in the sky, people began to generalize the concept. They imagined rotating lines or curves around a point, creating spheres, cylinders, and all sorts of 3D shapes. This leap from flat figures to imagining how shapes rotate was crucial. It connected the geometry of the heavens with geometry on Earth, leading to a deeper understanding of both structure and motion in our universe.
So that's what. And but who was the first to observe and write down the mathematical formulation for that?
When it comes to spheres, a major leap was made by the ancient Greeks. While early ideas existed, it was likely Euclid, around 300 BCE, who systematically wrote down geometric principles in his Elements. He defined the sphere mathematically, a solid figure formed by rotating a semicircle about its diameter. This formalization laid the groundwork for understanding spheres and other 3D shapes, and we've built on that ever since.
Okay, what was next big geometrical figure that they understood and wrote down the mathematics?
After mastering circles and spheres, the Greeks turned to the conic sections, the curves you get by slicing a cone. Apollonius of Perga, around the 3rd century BCE, laid out the mathematics of ellipses, parabolas, and hyperbolas. These shapes became fundamental for everything from planetary orbits, ellipses thanks to Kepler, to paths of projectiles. Each step added a new dimension to geometry's power.
So this is a conic section we are talking about, and means if there is a cone, if we cut in a specifically geometric way, we get the shape like ellipse, parabola, hyperbola. That is what you are referring to.
Exactly. That's the heart of it. When you slice a cone at different angles, you get those distinct shapes. A circle if you cut horizontally, an ellipse at a slight angle, a parabola if you cut parallel to the side, and a hyperbola if the angle is steep enough to slice both halves. This discovery wasn't just beautiful geometry, it became essential for understanding everything from planetary motion to satellite dishes. Geometry went cosmic.
But why they have chosen that cone at the first hand?
They didn't pick cones randomly. Cones were a natural shape found in everyday life. Think of lamps, pottery, even mountains. The Greeks, especially Apollonius, were driven by curiosity. They wanted to understand all the curves you could get from slicing such a simple shape. What they discovered was that these curves, ellipses, parabolas, hyperbolas, turned out to describe real phenomena, from planetary orbits to trajectories. In other words, they found deep connections between shapes and nature.
Yeah, that's a very interesting thought. Like orbits to trajectory, like those uh, those shapes, specifically this ellipse one is very interesting to understand that part. And what about but trajectory? I think the parameter what we give and the trajectory what we get and the results we compare with the shape or the geometry.
Exactly. In the case of trajectories, like a thrown ball or a planet in orbit, the shape isn't just a visual curiosity, it's a mathematical prediction. By plugging in parameters like initial velocity, angle, or gravitational force, we get a precise geometric path. For simple cases, like near Earth, it's often a parabola. For planets, it's elliptical orbits, as Kepler showed. So the beautiful shapes are the language nature uses, and geometry lets us read it.
The beautiful shape are the languages nature uses and the geometry let us read it. Okay, that's a very interesting thing. And what next thing they have observed?
Building on those conic sections, the next leap came with coordinate geometry, thanks to Rene Descartes in the 17th century. He realized you could describe geometric shapes with algebraic equations. Suddenly, lines, circles, and ellipses were not just visual, they were pairs of numbers on a grid. This fusion of algebra and geometry opened the door to modern mathematics, physics, and even calculus. Geometry was no longer just about shapes you could draw, it became about equations you could solve. And that changed everything.
Algebraic equations suddenly lines, circles, and ellipses were not just visual, they were pairs of numbers on a grid. Can you explain that part in more detail?
Sure, Descartes introduced the idea of plotting points on a plane using pairs of numbers, coordinates. For example, a point might be at 2, 3, meaning 2 units along one axis and 3 along the other. Now, a line could be described by an equation like y equals 2x plus 1. Every pair of x and y that satisfies it lies on that line. Similarly, a circle could be an equation like x squared plus y squared equals r squared. Suddenly, geometric shapes weren't just drawings, they were solutions to algebraic equations. This allowed people to analyze, predict, and transform geometry with algebra, bridging two worlds.
So,
So, from those humble geometric origins, we ended up with a universal mathematical language. With coordinates and equations, geometry became the foundation for calculus, physics, and beyond. It's what lets us understand orbits, build bridges, design computer graphics, all thanks to connecting shapes with numbers.
yeah, that was a very great idea about using plotting points on a plane using pairs of number. Why they have used pairs of numbers?
They used pairs of numbers because they needed a way to precisely locate any point on a flat plane. One number tells you how far to go horizontally, the x coordinate, and the other tells you how far to go vertically, the y coordinate. Together, they give you a unique address for any point. This system made it possible to describe geometric shapes using equations. A line is all points whose coordinates satisfy a certain equation. It was a revolutionary way to unite algebra and geometry.
Okay.
I'm glad that clicks. It's always fascinating to see how a simple idea, just two numbers, completely transformed how we approach shapes and space. Let me know if you ever want to dive deeper.
What about I one idea click on me just now, like we study basis states in quantum physics and linear algebra basically, but in quantum physics more like a application based, but the core idea comes from linear algebra. But is that somewhere related with this plotting points and something like that and coordinate?
It's related in spirit. In linear algebra, we use coordinates to represent vectors. Each vector is a combination of basis states. In quantum physics, basis states are like a coordinate system for the space of quantum states. A quantum state is a superposition, like a combination of basis states, just as a point is a combination of x and y coordinates. So while quantum states live in an abstract vector space rather than physical space, the idea of coordinates, breaking things down into components, ties back to that same conceptual foundation.
A quantum state is a superposition like a combination of basis state, but do this idea related with the early discovery of this what you mentioned about Rene, what was that?
Yes, conceptually, it's all part of the same mathematical lineage. Rene Descartes gave us a way to represent geometric space with coordinates. That same idea, breaking down a position into components, evolved into linear algebra, where any vector is a combination of basis vectors. Quantum mechanics applied this directly to abstract state spaces. So while quantum states are not physical coordinates, the principle of expressing something as a combination of fundamental elements traces back to these early discoveries of using coordinates to describe the world.
So geometric space with coordinate, that's a very intuiting idea.
It really is. From mapping the physical world to charting abstract quantum states, that idea of using coordinates to understand relationships is foundational. It shows how geometry gave us a universal toolkit for describing almost anything.
So, what was next? Another big idea from geometry.
One huge leap after coordinate geometry was differential geometry, pioneered in the 19th century by Gauss and later Riemann. It let us study curved spaces, not just flat ones, essential for understanding things like the shape of the Earth or Einstein's curved spacetime. Geometry became a tool not just for shapes, but for understanding the fabric of reality itself.
Can you give a bit more explanation?
Of course, differential geometry looks at curves and surfaces locally. Instead of treating space as flat, it considers how it bends. Gauss introduced the idea of curvature, showing that surfaces have their own geometry. Riemann generalized this to multiple dimensions, laying the groundwork for Einstein. In general relativity, gravity is seen as the curvature of spacetime. So what started with triangles on a flat plane grew into understanding the shape of the universe itself.
Can you, okay, we'll discuss this till later, but the idea of curve is just a, if we set some parameter, that parameter moves in time and space, then we get a curve like thing. The simple intuition.
Yes, that's a great way to think of it. A curve is basically what you get when you let a parameter like time or some other variable move along and it traces out a path. In space, that might mean a path in 3 dimensions. In quantum physics, it could be an abstract path in a state space, but at its core is that simple. A curve is the trail a parameter leaves behind as it moves.
Okay, what
I'm gl-
what major idea that differential geometry gives to us? Another big idea.
The big idea is that space itself doesn't have to be flat. Differential geometry allows us to understand curved surfaces, like the Earth or even the universe. This led to Einstein's general relativity, where gravity isn't a force but the curvature of spacetime. It's a shift. Instead of thinking of objects moving in straight lines, we see them following curves shaped by the fabric of reality. Geometry, quite literally, explains the shape of the cosmos.
But you mentioned about one thing. Riemann generalized this to multiple dimensions. Dimension. What was that?
Riemann extended the idea of curvature to spaces with any number of dimensions, what we call manifolds. He showed that you could measure curvature locally, even if the space is very complex. This paved the way for Einstein's four-dimensional spacetime, where time is treated as a dimension. In short, Riemann gave us the math to handle curved spaces of any dimension, letting us model the universe's shape and how it bends.
Okay, manifold is what, like, if there are two, three, more than two, three number of curves, then we get a manifold like geometry.
A manifold is basically a space that looks flat on a small scale, like a curve or surface, but can be more complex globally. Think of a sphere. Locally, it's like a flat plane, but globally, it's curved. In higher dimensions, a manifold might be more abstract, like the space of all possible states of a system. So it's not just multiple curves, but a whole shape or space that might have any number of dimensions in curvature.
So manifold might be more abstract, like space of all possible states of a system.
Yes, exactly. In physics or mathematics, a manifold can represent something like the space of all configurations a system could be in. Each point is a possible state. Even if we can't visualize it, the same geometric tools like curvature help us describe its structure. So manifolds give us a flexible, powerful way to understand all kinds of spaces.
One example from quantum physics, anything you can relate.
Sure, think about the state of a quantum particle with spin. The space of all possible spin directions forms what we call the Bloch sphere. Even though it's a sphere, it represents all possible quantum states of the spin. So in this sense, the Bloch sphere is a manifold. Each point on it is a unique quantum state, and the geometry helps us understand how states evolve or how measurements work.
Okay, can you give conclusion what we discuss?
We started with geometry's early roots, points, lines, and shapes for practical tasks. The Greeks formalized it with Euclid and conic sections. Descartes gave us coordinates, merging algebra with geometry. From there, we moved to differential geometry, understanding curved spaces and eventually manifolds. This abstraction lets us describe everything from space-time to quantum states. In short, geometry evolved from measuring land to shaping our understanding of the universe and reality.
You can give a quick intuition to understand point, line segment, and more. Like very quick.
Imagine starting with a dot, that's a point. Stretch that point in one direction and you get a line. Cut a piece out of that line and you have a 9 segment. Tilt or bend these lines and you start forming angles and shapes, triangles, circles, and beyond. Every complex shape is built from these simple beginnings, just points connecting into something more.
Okay, thank you.